classic methods problem here that I've been asked about a number of times over the years. So what we've got is a figure showing a rectangular field in which AB is 300, that's that, and BC, this total distance here, is 1100. So that's basically the properties of the field, the side lengths of the field. An athlete runs across the field from A to P at 4 meters per second. Find the time taken to run. So that's the speed, and we need to note that speed is distance over time. So what have we been given? We've been given the speed and we want the time. So let's transpose this to make time is equal to distance over speed. So we need the distance to complete this formula. So the distance is the length of this line here, AP, and we want that in terms of theta. So we're allowed to have an unknown in this distance. It's not like we're going to get out like, oh, the distance is 15 or something like that. It's going to depend on the angle, obviously. So let's get stuck into it and go time is equal to the distance. Well, that there is a right angle triangle. This is the hypotenuse. So we're going to say that we've got the adjacent over the hypotenuse, that's cosine theta is equal to the adjacent 300 over the hypotenuse, which is AP. AP is equal to 300 over cosine theta. So that's the distance of line AP is 300 over cosine theta, and we're going to divide that by the speed, which is divided by 4, or multiply it by a quarter. So that's going to be 300 over 4 cosine theta, 150, 75 cosine theta after the simplify. The athlete on reaching P immediately runs to C at 5 meters per second. Find the time taken to run from P to C. So athlete runs across the field, then hits this point here, runs along this line. So to get this distance here, what we're going to do, we know that B to C is 1100. And what we're going to do is remove BP. So from the total distance, if we remove this portion here, then we're going to get distance BC, distance PC rather. Okay, so how do we get this distance here? Again, it's some trig. O over A, that's tan. So tan theta equals the opposite, or BP, over 300. Therefore, BP is equal to 300 tan theta. And so the final formula for PC is going to be 1100 take away 300 tan theta. So it's distance BC, the length of that line, remove this distance here, will give us the distance. All right, and what we want is the time taken. So we recall that time is the distance over the speed. So time is equal to this distance, 1100 take away 300 tan theta, all over the speed, which the individual is doing, 5 meters per second. That is going to be 5 goes into that, 120, 20, 6 lots of 20, 6 twos are 12. I think it's 220. 220, take away, oh boy, 60 tan theta after dividing through by 5. All right, now what we need to do is use the results from A and B to show that the total time. So total time is going to be the time taken for section 1 plus the time taken for section 2. Now section 1, we've already devised that time is 75 over cosine theta, plus the other one is 220 take away 60 tan theta. All right, so I need to get this into this form, and it's got everything to do with tan theta. Now notice that there's a lack of tan theta in this answer here, and that's because they're going to use the identity sine on cos. So 75 cosine theta plus 220, take away 60 multiplied by sine theta over cosine theta. Now, what we've got here is 75 take away, because there's a common denominator here, we're going to say 75 take away 60 sine theta all over cosine theta plus 220, or the other way around as required. Whoops, that's a long vinculum there. All right, we want to diff it now. Okay, so dt d theta. All right, so what's going to happen is the 220 will chop out on the derivative, and we're going to diff this. I'm going to use the quotient rule to do it. I'm going to say that u is equal to 75 take away 60 sine theta, and v is equal to cosine theta. Du d theta is equal to, constant chops out, sine goes to cosine, negative stays there, negative cosine theta. Dv d theta is equal to negative sine of theta. Okay, and so what we're going to do is use the quotient rule on that, which is v du dx take u dv dx over v squared. Now, v du dx, so we're going to multiply those, which is going to be negative 60 cosine theta all squared, take away that, multiplied by that. Let's go negative sine theta multiplied by 75 take away 60 sine theta all over v squared, which is cosine theta all squared. Let's tidy this up a bit. So a negative multiplied by a negative is a positive. So negative 60 cosine theta all squared. Plus sine theta, 75 take away 60 sine theta all over cosine theta all squared. Okay, 60 cosine squared theta plus 75, so I'm just going to use the distributive law now, sine theta take away 60 sine theta all squared over cosine squared theta. All right, there's my derivative there. Now let's go to the calc at this point. Define f of x equals, where's my function? 220 take away, or plus rather, 75 take away 60 times the sine of x all over the cosine of x. We're in the right mode. Let's go and get some exact values. Okay, so now I'm going to diff it, which looks pretty much what we've got. They've yanked negative out as a common factor for whatever reason. Yep, 75, yep, because negative's out, that's a positive. That's our derivative. All right, now let's just see if that can be simplified at all. Whoa, massive simplify. Okay, so equals 150 sine of theta, take 120 over cosine 2 theta plus 1. All right, how do they do that? Well, I'm not 100% sure, to be honest, and it's probably using a whole bunch of identities that I don't really want to get into, okay? And I can already see that this is a calculator question by one of the other parts of this question. So I feel really comfortable going from that to that at this stage. unless there's something really obvious that I'm missing on the simplifiers there. Anyway, let's go ahead and continue. So dt d theta is that. Find the value of theta for which dt d theta is equal to 0 and show that this is the value of theta for which t is a minimum. Okay, so we're going to go 0 equals 150 sine theta, take 120 over cosine 2 theta plus 1. So all I've done is I've got my derivative here on the calculator and I'm just going to let it equal 0, i.e. dt d theta is equal to 0. So now I'm going to go ahead and solve. Now when I multiply both sides by this, that just chops out, leaving me with 0 equals 150 sine theta, take away 120. Let's solve that. 120 over 150 equals the sine of theta, which is 12 on 15, which is 4/5 equals sine theta. Now this is why I know we can go to our calculator at the moment, is because we don't know an exact value of 4/5, okay? So the exact value in theory is going to be the inverse sine of 4/5. But let's go ahead and solve this. So what I'm going to do is say that we're going to solve. The answer equals 0, so the derivative equals 0 for x, and the domain, because it's a angle that's between 0 and 90 degrees, we're going to say 0 less than equal to x less than or equal to 90, but we're in radians mode, so we're going to go shift and 0, which is pi on 2. Okay, so there is the exact value, of course, and the decimal B is that. So theta in radians is 0.92729 radians. We can get a degree measure on that. So I'm just going to ask the question in degrees mode, because if I tell an athlete to run 0.927 radians, they're going to look at me like, what are you talking about, mate? So I've gone over the degrees and changed the domain, and this is more appropriate. It's a 53.130 ... angle that the athlete is going to go on. I'm just going to check the answers in the back of the book and just see if they approximate at this point. Yeah, all right. So the back of the book does give that and that one, but there's no suggestion on why we should approximate. So yeah, where possible, give the exact answer. Now show that this is the value of theta for which t is a minimum. Look, the only way I really know how to show that that's a minimum is to generate a gradient table. So let's do that. So what I've got is different measurements for theta. We're going to jam them in dt d theta, and we're going to look at what the shape is. So let's put together our gradient table here to show it. All right, so this one here is a theta of 4/5. Okay, so when theta is equal to 4/5, no, it's not 4/5. It's when it's equal to the sine inverse of 4/5. Okay, so hang on, let me think about this. Okay, so it is the sine inverse of 4/5 is my value there. Now what we're going to do is just grab some values on either side of this. So this one here is 0.92. That's what the sine inverse of 4/5 are. So what I'm going to do is just grab a value a little bit lower than that, because remember what we've got here, we're looking at dt d theta versus theta. So these are different theta measurements. So I can give these in, actually I think I need to give them in radians. So I'm going to try a lower one. I'm going to try a half. Okay, so sine or a half is what I'm after here. So that's the radian measurement. And I'm going to choose a higher radian measurement there. I'm going to choose 0.9, which is higher. No, I'm going to choose something bigger than that. 0.95, which is larger than this value here. So let's jam in those into my derivative. So I'm going to grab my derivative function and I'm going to say, hey, what is your gradient when x is a half? And my gradient is, I'm in degrees mode. My gradient is negative 31.21 ... The point is I've got a negative gradient. All right, now I'm going to say, what's your gradient at sine inverse of the inverse sine of 4/5? And hopefully what this does is it says my answer is 0. Haha, it does. And that makes sense because that's where the stationary point is, or the minimum. Now what should happen here is, to show that it's a minimum, that should be a positive gradient. So the final thing I'm going to jam in is 0. The answer is 2.97 ... Don't really care what the value is. All I care is that I've got a positive gradient at this point. So that is, I believe, a good method to show that it's this value of theta for which it's a minimum, because beyond that, it's going to be larger values on either side. So when it's a half, it's going to be a negative gradient. When it is exactly 0.92729 ... or the sine inverse of negative 4/5, we're going to have a flat spot. And when it's larger than this value, i.e. 0.95, we've got this positive gradient over here. Okay, so in the previous questions, what we've done is found out the value of theta that will minimize the function. So now we just need to get that minimum value. So all we need to do is calculate t with theta equals, what was it, sine inverse of 4/5. So if we simply slap sine inverse of 4/5 into the function, we'll get the minimum value for t. So we'll do that on the calculator as well. I'm just going to do f of sine inverse 4/5, and we get 265. And I think that that's seconds. So find the minimum value of t and find the distance of point P from point B that will minimize the athlete's running time. So we just need to get that distance. So let's go back up to the original question here and have a look at that one. So we need, what was it, PC, or let's have a look, sorry, PB. So we need to get PB, this distance here. Now this distance here we got, there's BP there, so line BP is 310 theta. So let's go back down to the end here and do distance PB equals 310 theta, and let's sub theta equals sine -1, so the value of theta that minimizes the time. And we're going to find that PB equals 300 times the tan of sine inverse 4/5. So let's do that one there. So we've got 300 multiplied by tan of this thing here. Let's grab that and chuck that in there. And we get 400 meters in this case. All right, so there you go. There's a tough one.